Okay, so today's video is about oscillatory motion. Please excuse the background noise. They're doing construction in my house at the moment. I chose these two problems because I feel like these problems will give you a good understanding of all the formulas needed to solve these problems involving oscillatory motion. Problem number 1. A force of 500 newtons is used to stretch a spring with a 50 kilogram mass attached to it by 0.35 meters. What is the value of the spring constant, and calculate the frequency of the oscillator? So here we have a diagram. We have a wall and there's a spring attached to it. This is the mass. Now we're going to stretch the spring and we're going to apply a force of 500 newtons to stretch it by 0.35 meters. So how can we calculate the first part of this problem? It's asking for the spring constant. Well, based on Hooke's law, we know that F equals Kx. So in order to solve for the spring constant, we're going to have to switch the equation to K equals F over X. It's simply the force divided by the displacement. So for force, we know that it is 500 newtons, and from the displacement, we know it's 0.35 meters. Plug that into your calculator, and you will get 1428.6 newtons per meter. Next, it's asking us to calculate the frequency of the oscillator. Well, we know that the angular frequency is equal to 2 pi f. We're going to go ahead and solve for f. So we're going to divide both sides by 2 pi, like shown here. And then we know that f equals 2 pi the square root times the square root of k over m. The reason we put k over m is because we know that the angular frequency is equal to the square root of k over m. From that, if that makes sense, hopefully that makes sense to you. I'm going to go ahead and repeat that though. So we're going to start with this equation. We solve for f, and from this we get f equals the angular frequency divided by 2 pi, which would be 2 pi times the square root of k over m. And we know that the angular frequency is equal to that. Once you get that, you will go ahead and plug in what you do know. So we know K, we also know our mass. So it would be 1 over 2 pi times the square root of 1428.6, which we got from here, over 0.50, which was stated up here as the mass, and you'll get 8.51 hertz. That is problem number 1. The second problem here is going to be a little bit more complicated. I chose this problem just so you can get a basic understanding of more of the formulas used throughout this chapter. So this problem states a 0.75 kilogram mass vibrates according to the equation x equals 0.65 cosine 7.35 t. Determine the amplitude, frequency, period, and the string constant. I drew a little diagram here just for a basic understanding of what is going on. And this is the equation we are going to use to solve for these answers. This states that the current displacement is equal to the maximum displacement, which is the amplitude, times cosine omega t. And sometimes it does have a phase angle, but in this problem it doesn't. So we're actually going to be using this equation here, which is x equals the amplitude times cosine omega t. The amplitude is whatever number is set in front of the cosine. So for here we have 0.65. So the maximum displacement is 0.65, which means that x can be anywhere from 0.65, between negative 0.65 to 0.65. So if you graph this equation, the amplitude is going to look like this. Here you see the negative 0.65 on the graph and the 0.65 on the graph. The cosine graph usually starts at the top, and the graph will go ahead and oscillate between these 2 points back and forth. So here we solve for A already. So amplitude equals 0.65, and x can be anywhere between those 2 points. So now what does this 7.35 represent? 7.35 represents the angular frequency of this oscillator. If we know the angular frequency of this oscillator, we can also find out the regular frequency using this equation here. So from this equation, we know that the angular frequency equals 7.35 radians per second. Now we're going to go ahead and solve for that. So we're going to use this equation here. We're going to replace the omega with 7.35 equals 2 pi f divided by 2 pi, and here we get frequency equals 1.17 hertz. That is how you solve for frequency for this problem. Now, how can we solve for the period? For period, we learned that t is period, which t equals 1 over frequency. So since we know the frequency, we will do 1 over 1.17 hertz, and here we get 0.855 seconds. That is how we would solve for the period. And the last thing this problem is asking for is for us to solve for the spring constant. In order to solve for the spring constant, we're going to have to use this formula right here. As you can see, frequency equals 1 over 2 pi times the square root of km. K is what we are looking for. So in order to get to k, we're going to have to multiply both sides by 2 pi, like I did here. So we multiplied 2 sides by 2 pi, and we canceled that out. From there, we get 2 pi f equals the square root of k over m. We're going to go ahead and take the square of both sides in order to get rid of this radical. Once we do that, you're left with 2 pi f squared equals k over m. And then you again will multiply both sides by m to cancel those out to get k by itself. And then we finally get k equals m over 2 pi f squared. Remember that the angular frequency is equal to 2 pi f, so we can go ahead and replace the 2 pi f here with angular frequency. So we get k equals m omega squared. And then we know from the problem stated right here, the mass, and we also know the angular frequency right up here. So we're going to go ahead and plug in what we do know. We know the mass and omega, so we get k equals 0.75 kilograms times 7.35 radians per second squared. And finally, we get our answer. The answer is right here. Spring constant equals 40.5 newtons per meter. And that is how you solve for the spring constant. So from this problem, you were able to understand how to use the formulas that we learned throughout this chapter to solve for the amplitude, frequency, period, and the spring constant. Also, from the previous problem, I did show you guys a more simpler version, I feel. We were able to also learn how to use these formulas to solve for the spring constant and calculate the frequency of the oscillator. Hopefully both these problems gave you guys a basic understanding or a good understanding of all the formulas you need in order to solve problems involving oscillatory motion. Thank you.